I'm building a VPO Parker valve. So this is the VPO valve from Parker. It's a pre-comp proportional valve. This one has a electro-hydraulic proportional control. It has a pre-compensator. So the spool has a different type, depend on how much flow needed. Each section has a different flow, and also the type of spool. That's depend on the application. So you can check this in VPO manual. So I'm checking this, make sure the spool is free. Hey.
Hey, my teacher.
What happened?
There's one thing I don't understand.
Hmm.
For the road changer, why this one connected to the cylinder opposite way? So this one, so A go to extend?
So A. Extend and
Retract.
retract. So what happened is,
So one go extend, one go retract.
so it's gonna be, what is this here? Rod, cylinder rod changer.
So carousel swing.
So that will be like
Yeah.
that. But what's the position of the cylinder?
I think both are the same.
Are the same?
Mm.
It should be the same.
Yeah.
So that one there, because this circuit is a generic, they just copy it.
Yeah.
I think the position of the other cylinder is opposite, like back and forth.
Mm.
So it's kind of this one retract and this one extend.
Mm.
So it's the same. But if we putting the cylinder same position,
yeah.
it should be whatever on the piston side should be on the other side piston side. Otherwise, it won't move
Mm-hmm.
because it's counter.
So this one is. So this cylinder meant to be installed opposite.
But based
and-
on the other machine, they, as I look on the picture, they're the same.
Mm.
But the way they do this diagram
Mm.
is because it's a generic. They copy that from the original. So originally, yeah, maybe like
Yeah.
back and forth. So sorry about that intermission, guys. Still okay. Now I'm gonna put this. I don't know what is this, but this engage to the spool, and then when you do the manual operation, this link, it's a link. This will move the spool. It's kind of like this, kind of like that. So attach So this attached to the lever, and then the lever will move the spool forward and reverse. So it's not easy job because sometimes people will come and ask questions how the hydraulic works, so I need to help them. So that's why we need technician. We need more technicians, guys. Learn hydraulics because a few people know hydraulics. And then continue learning, study. I'm making sure that the slot of the roll pin is perpendicular or tangential so that it's more stronger. You just move the spool so that it will line up. Flush only. Once the roll pin is flush, and that's it. Double check. Make sure it's engaged. Yep, see? It's moving, so meaning it's engaged. That's how you check. Now you put the end covers or this end plate, the adjustment. So this one here you can adjust the So I'm checking that the O-ring is good, like it didn't nip after I push the plate. So you always double check your works. Putting out the circuit, I always use a safety glass when you install circuit, just for protection, safety. Push with the dip. Then you always turn the circuit, means the circuit is totally in, alright? Always double check your works. My circuit is a very small point. I don't have the next size, so it's trouble to put in. Make sure it's in. Turn. Yep. Can put the relief now. This is the ports relief. A and B. So this is the pre-comp spool. So the pre-compensator at neutral is open, and then it's positioned before upstream. So meaning this is before the metering orifice or spool. So that's why it's called pre-comp. It located upstream position before the metering orifice or spool. The post-comp, the post-compensator location is placed after the metering orifice. And then in neutral position, the post-compensator is closed. Okay? So the spool is moving, so meaning it's good. These are the shims. The shims purpose is to fine-tune the delta P. Again, the purpose of the pre-comp is to maintain the pressure drop so that you have stability and quick response on your system, because the flow is remain constant at constant delta P. So remember the principle, the delta P across the orifice is equal to the flow. Okay, so whenever your flow is rise, the delta P will also rise. So meaning delta P is proportional to your flow rate. So this guy here will maintain that delta P so that you have a constant flow rate regardless of the load downstream. Okay? So these are the shims. So the shims depend on how much delta P you maintain and also the flow. So let's say the delta P, let's say 100 liters per minute, this type of spool at delta P of 15 bar. So when the delta P is when the spring or the shim force is overcome by the pressure, then it will close your spool. So as long the delta P is maintained, the constant flow is maintained. Okay? When the delta P is higher than your spring force and shim, then it will change your flow. So, okay, these are the spring. They have two springs. The spring is to, so again, the spring, one is light, one is stronger or heavy. So the spring is the baseline force, the shim is the tuning for your delta P if you want to tune. So that delta P is proportional to your maximum flow rate across in this spool. So let's say this spool is 100 liters per minute at 15 bar delta P. As long that 15 bar is maintained, that flow rate will maintain. So that's the pressure comp. Put the plug. So pretty much, yeah, that's all the parts in one segment. And then the two solenoid here, proportional solenoid, which is your control to shift the spool. Yeah. And then this section here has 8 sections, so I'm building 8. Okay, for now, I will have a break. And thank you. This is the pre-comp spool. Consists of 2 springs. One is light and heavy, and then the shims. The shims is the fine tuner for the delta P. So if you want to increase your delta P, so you add more shims. If you want to decrease, then you remove shims. This spring here, this dual spring here is act as a baseline force, and then you tune with this shim. As you can, this is the valve here. So that spool is here, see inside, that's the spool. So the way it works, guys, like this. So I have a graph here, okay? This is the stroke of the spring, and then of course as the stroke reduces the pressure, the delta P will increase. So because it has a dual spring, it make a curve like this. It's more proportion to what the set should be. So this is the first set point spring, and then set point 2, which is the two spring, the inner and outer. So this is outer, and this is inner and outer. So since in the delta P across the orifice, okay, Q is always constant when delta P is remain constant, okay. So according to this principle, Q is proportional to your delta P. Now the CD here is the discharge coefficient. So in the orifice type, the sharp edge orifice around 0.5 to 0.6, but for the spool type, this is around 0.7 to 0.8, unless the Parker specified the discharge coefficients. So what happened is, if this is the pre-comp circuit, so normally the pre-comp is upstream before the metering orifice, means before the spool. So normally it's open, okay. Then this one here is your spool or metering orifice, and this is the spring, and then the signal that is count here up on this side, and then this one that's from your load, okay. So as you observe the diagram, the delta P is based on your metering on the control valve. So what happened if that spool, let's say the spool max flow is 100 liters per minute at, let's say, 20 delta P bar, okay. So at 20 delta P bar, or differential pressure 20 bar, okay, let's put it like this. If that pressure, delta P pressure, will maintain 20 bar, your flow will remain constant regardless of load here, okay, because the shim is set in that delta P. So once that delta P overcome, then the flow will decrease, okay, because remember here, based on the principle on the flow across the orifice, Q is proportional to your delta P. All right, so that's the pre-comp, that's the advantage here, because you can control the system accurately and the speed sustainably, and the speed won't affect regardless of the load, unless you have a two or more function simultaneously. If the pump supply is below the saturated pressure, then that's the time the system will affect. But without that happening, the flow will remain constant, okay. So that's the purpose of the pressure comp. Now let's say back to this graph. So the stroke of the spring is in relation to your delta P. Now, if you less the force of the spring, of course, your delta P will less. Okay? Once your delta P will reduce, then you can't get the 100 liters per minute even the spool is fully open. Okay? Now, this one here, assuming that the spool is remain fully open at 100 liters per minute, regardless of the load here, as long your delta P is maintained, the flow rate will remain constant. Now, what happened if you decrease the shim here? If you remove the shims, of course you will reduce your delta P. So expectedly you cannot attain 100 liters per minute, because according to the principle, Q is always proportional to your delta P across the orifice. The orifice now here is the spool. So the spool graph, guys, is kind of like that. So this is the stroke, and then this is the Q, millimeters. Okay, so the more you stroke the spool, the more flow you get. Okay, so now that's the you need to be careful, because sometimes also the more delta P, it will create heat energy loss on the system, so it will create heat. Now let's say your delta P now will become 10 bar. So assuming that the metering spool is fully open, so you have constant area, and then the delta P new will be 10 bar. The Q new is unknown. This is Q old, and this is delta P old. Alright, let's see what's the Q new if you change the setting of the spring. Okay, let's remove this one here. So there is our formula here. So the flow rate new is equal to Q max, or the original, and then times the square root of delta P new over delta P old. So since we changed the delta P to 10 bars, so that will be our Q new now is equal to 100 times square root of 10 over 20. So let's calculate that. So 10 divided 20, and then square root, and then you times that to 100. That will become 70.71 liters per minute. So, meaning the Q now will reduce to 70 liters per minute instead of 100 liters per minute. Even you open the spool all the way open or max, but the delta P now is reduced. So meaning this spool here is throttling the throttling and maintaining the delta P of 10 bar, because that is your setting, 10 bar. So what happened here, guys, let's say the pump supply 100 liters per minute, that's your max that's your max equal to your max spool as well. Let's say the max of the pump is 100 liters per minute, but your delta P is only 10 bar. So meaning what happened here? Oops, I have only 10 bars delta P. So what this guy doing is he gonna throttle the displacement or the flow rate until such time this one here, the P1 minus P2, the P2 is here, is equal to delta P, which is 10 bar. Balance that spring. Once that balance, so the rest of the, so let's say you're using a fixed pump, so the 30 liters per minute will now unload. Okay, If you're using a load sense type pump, then the regulator, this one here, will go to your LS. Let's say that one LS regulator. So the LS now will send signal to the pump, and then the pump off. It's only 10 bars there. Then what happened? The load sense spool on the regulator will move, and then it shift the pump to destroke a little bit to give 70 liters per minute. So that's how the pre-comp works. Okay, so this valve here, so you imagine, as you observe, this pre-comp is positioned upstream. So before the control spool or metering orifice, the post comp is downstream, so after the metering orifice. So you understand? So that's how it works.